briefly talk about elliptic curves to start off with, because they motivate what I'm working on. So basically, rational point. So rational point is just one on, so in this case, on a curve or a surface where all your coordinates are rational numbers. And by rational, I mean, so if my surface or curve is defined over a field, then that point is also rational. I mean, the coordinates are all in that field, so they're not over the algebraic closure of that field, they're actually in the base field. So yeah, we're going to start with an elliptic curve.
Sorry, Jenny.
Yeah.
I was given only one task and I failed in it,
No.
which is to mic you up.
Oh, okay.
So I'm very sorry about that.
Okay. So we start with our elliptic curve, and then we take 2 points on it. So you can generate another point just by simply drawing a line, a secant line through these 2 points. Then we hit the elliptic curve again here, and so we've generated a point R. Or equally, we could take another point here and take a tangent line at that point, and then we're going to hit our elliptic curve somewhere else over here, and we've generated another point. And it's like a fairly well-known fact that with a little bit of a tweak, you can turn this operation into a group operation. In actual fact, your set of rational points on an elliptic curve is an abelian group, a finitely generated abelian group. Now, the same is not true on a cubic surface, but it still makes sense. We can still define a secant and tangent operation in a way that makes sense, and then ask questions about the size of a minimal generating set of such points. But we have a few caveats that we have to state before we can define such a secant and tangent process. Because firstly, there are 27 straight lines that lie in the cubic surface, and so. Firstly, so say we wanted to take a secant line between 2 points, then we need to make sure that the line between those 2 points isn't one of these ones in S. But if it's not one of the ones in S, then it's fine. We're going to hit the surface again in another point, and we've generated another point. Equally, if we want to do a tangent process, then take the tangent plane at a point P, and then take a line. So we'd want particularly a rational line, so a K line, one which has its equations are defined over the field that we're interested in, and take any K line in this plane that isn't one of these 27 lines, see where it hits the surface again, and we've generated those points. Okay, and so basically we're interested in how many points do you need to start off with in order, by iterating this secant and tangent process, to get everything on your surface. Okay, so I said in my abstract that I'd give a partial answer to this question, and so here it is, this is a theorem by my supervisor. Am I writing big enough? Okay, good. So Samir Siksek, which says, let K be a field with at least 13 elements, and then let S be a smooth. If I forget to say smooth at any point, then everything I'm talking about is smooth. Smooth cubic surface defined over K. Suppose S contains a skew pair of K lines. Because these 27 lines are defined over the algebraic closure of K, so they might not all be actually in K. So we want a skew pair, and so skew, they don't meet each other. Because I should probably define what a cubic surface is. So cubic surface is defined by homogeneous polynomial in 4 variables, and it lives in 3-dimensional projective space. So if you don't know what projective space is, or you're not familiar with projective space, then you can just think about it as adding points of infinity that make things nice. So you would take something in normal 3-dimensional space, so just a cubic polynomial x, y, and z, and then by homogenizing it in W, you've added some points at infinity that just make your life easier. So that's what a cubic surface is. Yeah. So we want one which contains 2 skew lines, so they're not parallel, because things that are parallel in projective space actually meet at the point in infinity, and they don't meet each other. And so once we've got a pair of skew lines, then we let P be a rational point, a k-rational point on either, I'm going to call these lines L and L dash, on either L or L dash. Then the span of P, so I just mean everything you can get just by starting with P and then iterating this tangent and secant process, gives you all of the rational points on your cubic surface. Okay. So how did the proof of this work? Okay, so basically, the proof has 3 steps. The first one is you start with a point on one of your lines, so your point here, and then you generate everything on the line. The second step is you've got a line, and you want to generate everything on your second line, so you do that. And then your third step is, given two skew lines, you've got a point somewhere else on your surface, and you manage to generate that, and then you've got everything on your surface. Okay, so in this step 1, so yeah, firstly, if we think about a cubic surface, if you took a slice through it, so if you took just a plane and intersected it somewhere with your cubic surface, you're going to get something that looks like one of these. You're going to get a cubic curve. So it might look like one of these things, or if you're intersecting at a place where a point which was on a line and you were taking its tangent plane, for example, then you've got a line in there, so you've got a linear component of your cubic curve. So it might look like this. It might have a conic, so a quadratic part. Or possibly you might have this special case where you've just got it the conic is like tangent at any point P, you've got like a double intersection at P. Or you might have 3 linear components. And a special case of that being what's called an Eckart point. Yeah. And this is the worst you can get. So like an Eckart point here, point where 3 lines in S meet, and the lines are always coplanar when you have such a point. And that's kind of the worst thing you can get. And also, I forgot to put this in here, this P has to be non-Eckart. That's another condition on this theorem. And if you think about it, if you were trying to start with this point P here, and then generate more things via a tangent process, if you take any line through P, it's either going to be one of these lines, and then you get nothing, or it's going to be like this, and you don't hit anything else on your surface, because you've got like a triple intersection at this point P. So, yeah, so we don't want an Eckart point to start off with. Okay. So, yeah, but our tangent plane at P is going to, the intersection of it with the surface is going to look like one of these 3 things. So actually what we did in step 1, the important part in a way is that we got this line, but what we actually did is we managed to say, for example, the intersection of the tangent plane at P and the surface look like that, then we actually managed to get everything on the intersection of the tangent plane and the surface, which I'm going to call gamma p. So gamma p is just this cubic curve, which is the intersection of the tangent plane at p with the surface. Okay. So, now what I've done might not seem that exciting, but basically what I did is I replaced this 13 with a 4. So, I also did it for 2 and 3 as well, but I needed to add some extra conditions, so I'm not going to do that. So in order to do so, I kind of had to modify the proof. And so I'm going to show you what I did for step 2. So assume I've managed to do step 1. But so for step 2, so what Samir's proof did, it basically was just a point counting exercise. Because we had a pair of skew lines like this. You can take any non-A-cut point on the line and generate everything on its tangent plane. You've got a maximum of 10, because these lines are over the algebraic closure of K. So you've got a maximum of 10 K lines that are going to bother you and stop you doing what you want to do. So, yeah. So say you had, because what you want is you want to hit a non-A-cut point. What you want to do here is you want to get from a point on here, and the tangent plane here is, so any line is going to either lie in a plane or go intersect it exactly once. We know that these two lines are skew, so if you take a plane that contains this line, then it does not contain this line, which means it intersects it exactly once, which means it hits one of these points. Okay? And so what you want to do is manage to hit a point on here that isn't an A-cut point, and then you win because you've managed to, because then from that point you can generate everything on this line here. So it's kind of, yeah, so say you've got your 10 points through this line here. So we said here you've got exactly 10 other lines in S. These come in pairs, which are coplanar. So say you had something like this. This is kind of your worst case scenario. These are our 10 lines. Ooh, oh, that's not very. Okay, and then say all of these points that they hit over here were A-cut points. So then, if we take this point, we generate all of this. So say we started with this point, for example, and so we've got all of this line here. And when we said, okay, well, we can get all of this gamma p here. Oh, but hang on, we've hit an A-cut point. That's no good. Okay, let's try this point here. Generate all of this gamma p. No, we've got an A-cut point again, etc. But if you've got at least 13 elements, in fact, the 13 was needed for step 1, but if you have at least 11 elements in your fields, then you've got another point on this line, because the line is just a copy of P1, just which has so the size of, if you call the, like, say if the size of your field K was n, then this line has n plus 1 points on it. And so if you're talking about a finite field, if it's not, then we've got infinitely many points, so we can always find another point. So as long as we've got a big enough field, then we can find another point here, and then the intersection of its gamma p is going to be an intersection of a line and a conic. So we're going to hit, so this, sorry, should be like that. So it's just hitting this point here. Okay, so now suppose that was an A-cut point. Well, firstly, there's a rule that says that you can only have 5 A-cut points on a line, but I'm going to just gloss over. Oh no, I can say that because I've hit all of these lines here. And I said there were 10 lines in S. Oh good, I thought I was going to have to prove something, and I'm not going to. So we've hit all of these 10 lines which intersect this line here. So therefore, this one's not an A-cut point. Hooray! We've generated all of this. So we've generated this point here, which means we can get all of this line here. So it's just kind of a point counting exercise is the way that Samir did it. So if you've got enough points on your line, then you can get the other line. And so this is where the difficulty comes in with smaller fields, is you have to come up with something that allows you to get around the fact that you've not got very many points to play with. So I'm going to show you what I did. Okay, start over here. So basically, I found that you couldn't always show that these two lines that you started off with, you can manage to just start with any line and generate everything that's on a line skew to it. But if you do have a set of skew lines, so I came up with this lemma that basically says, so size of our field is greater than or equal to 4, and S is a smooth cubic surface again. And then we suppose it contains a pair of skew lines again. And we've got a non-ACART point P, which we're just going to say is on L. Then there exists a skew pair of lines which may or may not be equal to this pair of skew lines, such that all of the rational points on those two skew lines are in the span of that point P. So we're still going to be able to start with a point P somewhere on our line here and then end up with two skew lines for which we've generated everything. It just might not be the two skew lines we started off with. So that's enough for us to be able to move on to our step 3 and get everything we want. Okay, so, and here's the proof. So we start off with a pair of skew lines. This is L, and this is L dash. And we've got everything on L. Okay. Right. So we take a point P here. So first, let's suppose that the intersection, that its gamma P is something like this. So it's a conic, it's a line and a conic. Okay, so we've got everything on here as well. Which means we've generated this point here, which I'm going to call Q. Okay, so suppose Q is an ACART point, because we don't want it to be an ACART point. So then we've got a line here. It's got two lines going through it. Now, like by the same logic as before, so these three lines all lie in the same plane, and this line here intersects it exactly once. And we know that this line is in the surface, and this is the intersection of the surface of the tangent plane. So it must intersect one of these two lines here. So let's say it's this one. Okay, and let's call this point R. Okay, but then this point R here, if we look at these two lines, must both be in its tangent plane. So if we you can kind of see that, because if you think about it here, if you took like a limit of like how a line intersected these two lines here and took it as it went to R, you can kind of see that it has a double intersection at R. So therefore, these two lines both lie in its tangent plane. So therefore, there's another line in its tangent plane, because its tangent plane is the intersection of its tangent plane with the surface is a cubic curve. So there's another line something like that, or it might be an echo point. But that means that actually, so we had that if you took gamma p and intersected it with L dash, then you got Q. But now we've got the gamma r and you intersect it with L dash equals Q. And it's a bit of a subtlety you have to think about, but it is kind of elementary. But this is a contradiction because each point on here, they just in pairs, they have the same tangent plane. You can't have more than two having the same tangent plane. So this actually means it's a contradiction. So this point here can't be an Eckhart point. Okay, so if we start off with P such that gamma P is the union of a line and a conic, then we don't hit an Eckhart point and we're done. Great. So we must assume that our point P, I'll just do it again over here, is actually its gamma P is something like this. Okay, so suppose that this is an Eckhart point again. So we've got a Q over here, and we want this to be an Eckhart point. And in fact, we have to assume that every point on this line, because as soon as we've got one on this line that's like this, then we've hit a non-Eckhart point. So in fact, we need to assume that every single point on this line has another line going through it. Okay? So any other point on this line has got another line going through it. So now, we have a limit to the number of Eckhart points we can have on a given line. And basically, you can either have, if you always have that one point there's just exactly one point with a given tangent plane. So when you're in a case where either all of your points on your line are Eckhart points, or they're like this, then you can have up to 5 Eckhart points over your ground field. But otherwise, you're going to have either 1 if you're in characteristic 2. Characteristic 2 is when in your field you've got 1 plus 1 equals 0. Or you're going to have up to 2 if you're in any other characteristic. So by the existence of a non-Eckhart point on this line, but we've also said that we must have that every point on the line is intersected by another line, we've discounted this case where you can have up to 5 Eckhart points. So we're not in this case, which means that we've got enough, basically that means that we've got enough points on this line, because, so we just ignore this now. So we're going to have 5 points on the line if we're in the finite field of size 4, and we're going to have more points than that if we're in any other field. So basically, it means that we've got enough space that there's another 2 points like this that aren't an Eckhart point. Okay, so I hope that was clear. But then, so say this hits an Eckhart point as well. Well, we're okay because this line here and this line here are skew, and we've got everything on this line and on that line. So we've completed this lemma. Okay, so that's kind of a bit, just trying to give you a bit of a flavour of how some of these proofs work. So this was completed and written up into a paper, which has just been accepted for publication in Archive des Mathématiques. And now my work has diverged a bit more from what my supervisor has been doing, because this was just kind of an extension of his theorem here. But so he has shown that over Q, if you take a cubic surface over Q, then there's a family of cubic surfaces for which you give him a number and he'll give you a cubic surface for which you need at least that number of points to generate everything on the cubic surface. Whereas there's a conjecture that over finite fields, so long as the surface is smooth, so this doesn't work over F2, we have counterexamples over F2, but I think for F3 and above, and certainly for, well, conjecture, I'm much more certain over at least F11 and above, then you only ever need 1 point to generate everything on your cubic surface. And so that's what I'm working on at the moment. Yeah, and thank you very much.
Excellent. Other questions?
Yeah.
So this is over finite fields.
So this is over any field with at least 4 elements. But what I have been working on this thing where I think you only need 1 point to get everything, that's for smooth cubic surfaces just over finite fields, because over Q we can give you counterexamples to that. So
What about R or C?
but the number of points you'd need to, well,
Just in general, I mean.
so this theorem works for any field so long as you have at least four elements in your field. Yeah, that is quite, it's not a very,
So there's no restriction on the characteristics.
no. It works over characteristic 0 as well. Yeah.
Another question? So you mentioned at the beginning that if you've got an elliptic curve, that's a finitely generated abelian group,
Yeah.
right? But you said for a cubic surface, that's not true. Is it that that's not known to be true, or is it known
It's
to be
definitely
not
not.
true?
It's definitely not true.
Because of course these are examples where it is, right?
Well,
But now you're generated by a single element. It's a cyclic group, right?
well, it's not a group operation. 'Cause
Oh,
it's
I
not
see. I see.
well defined, I guess. Because if you stick P in twice, then you get like a whole set of points, right? Because if I started off with so say just like one of my examples I had before. So basically, if I started off with this point P, how I would generate everything, and it's in this gamma P here, so the intersection of its tangent plane, everything, all the rational points on here, is so if you take any rational line in its tangent plane, so say I took this line here, then you can hit everything on this conic except that point there. And then in order to get everything on the line, you just take pairs of points like this and draw lines through them, and then you get everything on this line here. And then you need a little fiddle to get the last point, but you can get the last point. So it's not, so therefore just by sticking P in once, you can get everything on its tangent plane, but straight away you get everything on this conic apart from just by one operation, so it's not like a well-defined binary operation. It does have a structure on it, which is called a Moufang loop, which is a non-associative algebraic object that Manin seems to like. That's how he does his work with cubic surfaces. I've not really done much of that kind of thing. Like a lot of the work that my supervisor and I have been doing has been to avoid having to deal with non-associative algebra. But yeah, so it's not actually a group structure on the set of points. So, yeah.
Other questions? Okay, now let's thank the speaker again.